I'm Nick Johnson. I'm the NASA Chief Scientist for Orbital Debris, stationed here at Johnson Space Center.
My name is Christiansen, and I work here at the NASA Johnson Space Center, and my job is to design MMOD protection and to do risk assessments for micrometeors and orbital debris.
The meteoroid environment, of course, has always posed a hazard to NASA spacecraft, and we've been concerned about that since the 1960s. But beginning in the 1970s, as the orbital debris environment, the man-made junk in space, has increased and accumulated, we have been taking a little bit more action and investigation as to that problem and those risks that might be posed. So we spend thousands of hours doing observations of the environment from ground-based radars, which can detect particles as small as just a few millimeters. And we work very closely with our DoD colleagues who have a responsibility for tracking the larger objects, those objects which are typically about 10 centimeters and larger. Over the last few years, the orbital debris environment has suffered a significant increase, primarily due to two events. One was the execution of an anti-satellite test by China in January of 2007. That occurred at an altitude of 850 kilometers, but the debris created during that event was thrown into very different orbits, both higher and lower, and threw debris down to the human spaceflight regime, well below 600 kilometers, and in fact posed a transitory increase in risk to the International Space Station and all the subsequent shuttle missions. And then in February of 2009, there was an accidental collision between a U.S. spacecraft and a Russian spacecraft at an altitude of about 800 kilometers, which created two more clouds of debris. And those two events, the intentional anti-satellite test and the accidental collision, have added about 50% to the known cataloged objects which are being tracked by the Department of Defense.
I'd like to show you what happens when hypervelocity impact hits the spacecraft. And what we'll start out with first is what we call a monolithic shield. So it's a single wall of aluminum. And I want to show what happens when a 1/8 inch particle or a 3 millimeter particle hits a half inch of aluminum at 7 kilometers per second. So this is a half inch of aluminum, and it was impacted with, it's hard to see, sorry about that, but with an 1/8 inch aluminum ball, about 3 millimeters. So it was 1/4 of the diameter was 1/4 of the thickness of this aluminum. And you can see that there's a crater in the aluminum, and on the back side it blew off the back. So there's not very much left. It almost went all the way through at 7 kilometers per second, straight in. Orbital debris can hit us at much higher velocities than 7 kilometers per second in low Earth orbit. It can hit our spacecraft up to 15 kilometers per second, maybe even a little higher. It depends on the trajectories of the spacecraft and the particle that's impacting you. But at higher velocities, this particle, same size particle, would go right through this half inch of aluminum. So this is maybe not a very weight-efficient way to stop a high-speed particle. So let me show you what happens when a 1 centimeter particle impacts aluminum. This is the size particle that we need to stop in order to meet requirements on space station. So 1 centimeter, about 3/8 of an inch of aluminum. At 7 kilometers per second, hitting directly into this 1.5 inch thick of aluminum, it puts a crater in the front, and on the back is what we call detached spall. It blows off the back. There's not very much left with this at the bottom of this crater, and hitting a little bit higher velocity would put a hole all the way through. Hitting it with a little bigger projectile would put a hole all the way through this particular target. And in low Earth orbit, we can get hit by a higher velocity particle. 7 is about what we can get with the ground tests, but on orbit we're going to have to defend against particles that go even higher, up to 10, 14, 15 kilometers per second. So these kind of particles would go all the way through this piece of aluminum, and we couldn't possibly launch this thickness.
during the 10-plus years of on-orbit experience with the International Space Station, we've seen a lot of damage to the exterior of the International Space Station. We've had a lot of debris hits. Most of them have been sub-millimeter particles. But it turns out even a small particle can wind up giving you a problem that you had not anticipated. One of the things that we discovered a few years ago was that some of the gloves on the EVA suits were coming back with small cuts on them, which potentially, of course, hazardous to the EVA crewmen. And one of the astronauts was able to find what was a particle impact on one of the rails near the exit of one of the EVA modules. And that impact was caused by, we're not quite sure if it was a micrometeoroid or orbital debris. We haven't been able to go in and examine it that carefully. But it created a large ring around the impact with very sharp edges. And those edges were the ones that were, we believe, causing the cuts in the gloves. So even very small impacts can cause significant problems from an operational standpoint. We see a lot of damage, of course, on the solar arrays because of the acreage there and the probability of collision just because of the number of square meters involved. We've seen a larger impact on one of the thermal blankets on one of the Russian modules that if it had occurred in another place would have been a much more serious situation. There are also issues. We have special dedicated shields on some critical components outside the space station, like the control moment gyros and other fluid lines and whatnot, because you can have a particle strike there where you have stored energy, either in a fluid or stored energy in a tank or in a gyro, that will have an immediate secondary consequence should that vehicle or that component be struck. Another issue that we're worried about, of course, are tanks, pressurant tanks or propellant tanks. And some of the latest designs for those tanks are using a relatively thin metallic shell with a composite overwrap. And there's a lot of pressure involved. And so if you get a small particle hypervelocity impact on that composite overwrap, then it can sort of unzip or come apart very energetically. And you not only have a problem from the overwrap, which is now free or coming off at high speed, you now have a loss of integrity in strength of the tank itself. And depending upon the internal pressure at the time, that could lead to a breach as well.
We also knew that the meteor and debris environment is very directional. You get 20 times more impacts on the front than on the back. We know that from LDEF, the Long Duration Exposure Facility. It came back with 20 times more craters on the front that we counted than on the back. There was 200 times more craters on the front of LDEF than facing Earth. So it's very directional, the threat.
There have been some very detailed probabilistic risk assessments for the entire Space Shuttle and International Space Station programs. And whenever we do those risk assessments, we take into the risk of all the other elements of the vehicles. And for the Space Shuttle, of course, that includes the launch risk and the reentry risk and on-orbit risk. Orbital debris turns out to be the number one risk to either the shuttle or to the International Space Station. So it's a significant issue for NASA to address and try to minimize. Clearly, we are concerned about that same risk for future vehicles, particularly for human spaceflight. And we are working very closely right now with the Constellation program to look at what the requirements are for the Orion vehicle. There are obviously two primary missions. One is to go to deep space, but one is also to service the International Space Station. And it turns out that from a protection standpoint, for the vehicle design, it's the space station mission which is the driver, because the vehicle needs to be rated for at least 6 months in low Earth orbit attached to the space station. And that presents the greatest risk of all of the mission scenarios so far contemplated for Orion. So we have to look at, again, all the sensitive areas. of Orion, obviously the heat shield, but other parts of the command module while it's on orbit to find out, what portions of the vehicle are most susceptible. You have to worry about the surface module because you can't have a penetration there and penetrate or damage some critical component inside the surface module.
For MMOD protection, what we want to do is use shielding effectively, put it where you really need to. You would like to use operations judiciously. If you can use attitude to provide protection, we want to do that. And then we would like to use detection systems in order to find and leak quickly and mitigate that leak as fast as possible. With spacecraft, what we want to use is we want to put a shield out in front, a bumper, we call it. And we put it a distance away from the pressure wall of the spacecraft. That's called a standoff. So what I want to show you is a more weight-efficient way to stop the same size projectile. And this is called a Whipple Shield. And it's got what we call a bumper out in front. So it's a thin layer of aluminum. And it was impacted again with the same size, 1/8 inch BB size projectile at 7 kilometers per second. It leaves a much smaller hole now in the outer bumper because it really doesn't deposit much energy into that bumper. The bumper's purpose, it's very thin. It's only 1/5 the thickness of the particle we want to stop. The purpose is to break up that particle, to shock it. And that's what it does. It breaks it up, and you have a gap or a standoff, and it spreads then the mass of the projectile and all that kinetic energy across a wide area of the rear wall. This would be the pressure shell. And so you can stop a very high-speed particle as long as you sacrifice volume. You need that gap. But you can do it with much less mass. See, the combined thickness of the front bumper and the rear wall is much, much less than that 1/2 inch of aluminum that we had before. We can get by with much less than 1/4 of the total mass of a monolithic shield. But even so, you need quite a large gap. It's preferred to have 30 times the diameter of the particle you want to stop in order to get a weight-efficient design. In some places on space station, we wanted to stop not this size, 1/8 inch, but we wanted to stop nearly 1/2 inch, so 4 times that size. We wanted to stop that type of particle in order to meet requirements on space station, and we only had 4 inches total gap. So the way that we did that was to add layers of ceramic cloth and Kevlar in between the outer bumper and the inner pressure wall on space station in order to meet the requirements and stop that size projectile. And that's what we call a stuffed Whipple Shield. Areas where we're going to get the most amount of hits, and meteors and debris impacts are very directional, and we're going to get hit more on the front and on the port and starboard side of a spacecraft that's flying, with one in a controlled manner with one surface flying forward. So in the front and on the sides, we put what are called those stuffed Whipple Shields with the Nextel, the ceramic cloth, and the Kevlar in between the outer bumper and the inner pressure wall. This is the stuffed Whipple Shield. Again, it's got an outer bumper. It was hit with this 1/8 inch particle. This particular test was at 7 kilometers per second at a 45-degree impact angle coming off from the normal. And it left a small hole again on the outer bumper. Here's the Nextel. And the Kevlar on the back side has a hole, and we stopped this size particle on the back. This was with a very short standoff, less than 2 inches. This is a 1/3 scale version of what we have on space station, protecting the U.S. lab and the airlock. very similar designs of protecting the Japanese modules and the European modules in the front of space station. When we say 1/3 scale, everything is scaled by a factor of 3. The gap or the standoff is scaled. The thickness of the layers are scaled, and and the particle as well. We often will look at new designs using a subscale approach because we can do more tests. We can shoot small particles more often in the laboratory with the light gas guns that we use, and so it's cheaper and more effective and efficient to go ahead and look at new designs subscale, and then look at a full scale later where we have to use larger guns, where we get fewer tests and they're more costly after we sort of work out all the bugs with the subscale versions. We often make spacecraft, at least parts of them, out of honeycomb panels. And honeycomb are very lightweight, stiff structures, very strong. So they are a good option to build spacecraft out of honeycomb. The problem when it comes to meteoroid debris protection with honeycomb is channeling by the honeycomb. And what we see here is a hole caused by an 1/8 inch particle, about 3 millimeter size particle. And in a Whipple Shield, we saw once we hit that front bumper, the particle breaks up and it spreads across the gap or the standoff, and that made it more effective than to have that spreading of the debris cloud. In this particular case with the honeycomb, you don't get that spreading. You get channeling due to the honeycomb, and so we have a small hole on the outside, and I'm not sure if you can see it, but there is a hole on the back here, and the witness plate back here, this would be the inside of your spacecraft, has been damaged, and you might see that little dent there. So this was penetrated all the way through by this 1/8 inch particle, this piece of honeycomb. Now, there's another way to build lightweight sandwich structures that are stiff, and that's to use open cell foam, metal foam. And we have the same weight panel here, one made out of honeycomb, one made out of metal foam core, and the particle impacted on the front, same size particle. Put a hole in it. The open cell foam allows the debris cloud to spread on the inside, and it's also all these little particles that are created by that first impact are hitting each of the cell walls within this open cell foam, and it's causing further breakup, and it is much more effective than the honeycomb at breaking up the remnant debris particles in that debris cloud. Anyway, there's no penetration of the rear face sheet. I can see a very faint little dent on the back, so a little bit of material made it to the last layer here, but it didn't go all the way through. And your inside of your spacecraft is completely protected. So this is, from an MMOD standpoint, is a better, more effective structure.
We normally divide the risk to our NASA vehicles into two categories: those which come from particles which are larger than about 10 centimeters, and those which are smaller than 10 centimeters. DoD tracks those objects larger than 10 centimeters with a wide variety of primarily radars deployed around the world, and they are now tracking roughly 20,000 plus satellites on a daily basis, maintaining those orbits. And they, for us, do what we call conjunction assessments. And every day, and sometimes, particularly for the International Space Station and the Space Shuttle, multiple times per day, they make assessments as to when any of those large particles might come close to either the station or the shuttle. We normally do this on sort of a rolling 3-day window looking into the future, so that we always have time to determine whether or not this conjunction is going to be a hazardous conjunction and which might require some sort of countermeasure. Normally that countermeasure is simply a collision avoidance maneuver. So normally if we identify an object about 72 hours in advance that it might be coming close to, for example, the station, we then work with DoD to collect additional information. We do higher fidelity modeling of both the objects and find out whether or not it's really going to come close. And typically close is within about 1 kilometer or so. We actually have a criterion of a risk of 1 in 10,000, which will require a collision avoidance maneuver by the station or by the shuttle. However, we also have a threat from those particles which are less than 10 centimeters. The International Space Station and the shuttle have regions on them which are vulnerable to particles as small as about 3 millimeters. We have protected a good number of the surfaces, the critical surfaces on station, up to about 1 centimeter particles with dedicated shields. But there are some critical areas, particularly on the Russian side, which are vulnerable to millimeter class particles. So these particles, again, can cause serious damage and potentially the loss of the use of the station. And so we have to have an understanding of what the risk posed by those particles are. So NASA undertakes a program to characterize the environment for particles less than 10 centimeters using ground-based radars, both DoD radars and radio telescopes actually out at JPL, the Goldstone radio telescopes. We use them in a bistatic mode to be able to see the smallest objects. And then we can develop a statistical environment that tells us how many particles there are at the shuttle and station altitudes. And by knowing exactly the orbits that we're flying, how long we're flying, how much critical area both vehicles present, we can determine what the risk is to those particles. Now, there's not much we can do about the environment, at least not yet. So what we have to do is worry about how we design the vehicles and how we fly the vehicles.
For the shuttle, the way to provide protection when you can't add shielding is attitude control. You want to fly attitudes that are more benign. You want to make sure that the strongest part of the vehicle is facing forward and the weakest part is facing aft or facing Earth. And on space station, when it docks, what we've done, because it's a short duration mission, the shuttle comes in and it docks to station with the belly facing forward and the very vulnerable wing leading edge under surface, the bottom of the wing leading edge is facing forward. So that's the worst attitude basically for the shuttle. But very soon after docking, the whole stack flips backwards so that the belly and the sensitive surface is facing aft. And that cuts down the risk by a factor of nearly 10 for the shuttle from MMOD to do that basic maneuver. And when we're not docked to station, we fly with the tail facing forward because, again, the wing leading edge then is facing aft, and the engine bells, which are used during launch, they're facing forward, and they provide basically shadowing or protection for the shuttle. So those are the ways to minimize the damage to the shuttle from MMOD with attitude control.
Prior to every shuttle flight, whether it's going to the International Space Station or doing some independent mission like servicing the Hubble Space Telescope, a risk assessment is performed to determine a number of criteria. One is, what is the risk of catastrophic failure of the vehicle due to orbital debris? A second one is, what is the risk of a penetration of the thermal control system of the orbiter, particularly the tubes inside the large radiators on the inside of the shuttle cargo bay doors. And we also do a metric looking for how many windows we're likely to replace because of small impacts by debris. Of course, the most important one is the catastrophic risk number, which we prepare. And there is a set criterion that we try to stay within to minimize the risk to the crew. And this takes into account the length of the mission, the altitude of the mission. Going to space station near 350 or 400 kilometers gives us one environment. If we're going to the Hubble Space Telescope at 600 kilometers, then the environment is a little bit more of a threat, and so there's a larger flux and the risk is greater. As I mentioned before, we have some luxury in flying the vehicle in different attitudes to put the less sensitive portions of the vehicle in the direction of the greatest flight. We actually do a very complex computer analysis using a code called Bumper, which actually looks at the orbiter and how it's being flown at 5-minute intervals throughout the typically 2-week mission. What is the orientation of the vehicle? What's the altitude of the vehicle? What is it doing? And then we accumulate the risk in each of those 5-minute increments and then come up with an overall risk for that particular mission. After the Columbia accident, we reevaluated the risk of the orbiter to impacts in general. And we found that there are some areas on the shuttle which may be a little bit more susceptible to particle impacts than we had determined previously. And so to be able to manage the overall risk to the orbiter, one of the processes which was introduced was OnOrbit Inspection. Of course, everyone is familiar now with the inspections which take place the day after launch, where we're looking at potential impacts from particles coming off the external tank, striking the orbiter on the way up. But just as important, and in some respects maybe even more important, is the inspection which is conducted on the day prior to re-entry, because that's the time when we're looking for potential damage which may have been created during the mission on orbit, whether, again, independent flight or at the International Space Station. So a very detailed inspection is undertaken, and we now have the capability to repair a certain level of damage. And by taking our operational measures and coupling them with our ability to repair certain levels of damage, we can now keep the missions within the required risk categories and not have too much of a risk for the crews.
We're looking at other types of ways to stop leaks in spacecraft, and one way to do that is to build patch kits and repair kits to stop a leak. Another way that we've examined is to add a layer on the inside, a liner on the inside that would seal or close a hole. And these liners are, I brought part of it really. This is an ionomer plastic. It has ion endings in the plastic, and there's a charge within the plastic, both positive and negative, and it tends to want to self-seal or pull together once you put a hole in it. It's just the nature of it. And so it does that. We add a backing of high-strength fabric and combine the two, and we've tested such a system, and it can close a 1/4-inch size hole as long as the delta P is on the order of 1 atmosphere. We're always looking for other ways to reduce the risk from MMOD, and another way to do this is to know that you've been impacted. If you were on a space station or a spacecraft that was going to the moon, going to Mars, and you had a hole in the pressure shell, you would like to know where that hit was. So you can react to that, to close hatches or add a patch to that hole to stop that leak. And so impact detection is a key thing for that, for a spacecraft like that. And impact detection is also very important for a reentry vehicle, because you would like to know if the thermal protection system has been compromised prior to reentry. You can do the inspection visually, or if you have sensors on board to detect the impact, that's the way that we would want to do it. Is to have sensors detect the impact and then go with the inspection later, after you've gotten a detection, and determine whether that damage was critical or not. What I wanted to show was that this is one type of detector. There's many different kinds, but one type is a film that once it's been impacted, it can be determined that there's been an impact on it, and this is a piezoelectric film, and so any movement of this piezoelectric film induces an electrical signal that you can determine that it has been hit. And if there's any hole in this piezoelectric film, it even gives a higher signal. So this kind of film can be added to thermal blankets, and then you would have to monitor then the film, the state of the film, or it can just be added by itself in a spacecraft. But there might be even lighter weight solutions, little microphones that pick up the noise. There's a very high frequency noise, so ultrasonic detecting sensors, and these are just basically little microphones that can be attached to the panels and listen for impacts. So that might be even a better approach, and in fact is used on the wing leading edge of the shuttle. One of the key things that must be done with MMOD protection is have a clear requirement for protection, a very firm, clear requirement for protection. In station we had that. We developed good shields in order to meet that requirement. With shuttle we have a requirement, and we developed operations to meet that requirement for protection. And for Orion we have the same thing. And so that's just fundamental, to have a good, clear requirement. Sometimes that's not really recognized, and so I wanted to say that. Another lesson is to do a risk assessment, to find out what your risk drivers are. You know, a lot of times on a spacecraft, when you first start out, you might think, oh, everything is broken, we've got to put shields everywhere, you know, we have a big mess. But in reality, usually a lot of the risk is once you do a risk assessment up front, you can find out that there are just parts of the vehicle that are very vulnerable to MMOD, to the problem. And you want to focus your attention on those risk drivers. It sounds simple and easy, but you just got to keep that in mind, that you want to find out what your risk drivers are, and then you just want to focus your attention on them, and try to either show that from further tests and analysis that they're not as bad as what you thought, or if they are from your test and analysis, then add shields to them or design a way through operations to mitigate the risk to those risk drivers in order to meet requirements. And I go back to those requirements because they're just absolutely fundamental. You know, you can't know how much shields to add or how much effort to put into the operations unless you have a benchmark to compare it to, and you need those requirements in order to know how much protection to add or how much effort to put into the operation side of the house in order to meet those requirements. So those are the two main things: is to find out your risks, you know, to have a requirement and do an upfront risk assessment to find your risk drivers, and then you repeat that process, really, at least the risk assessment part, as you go. You do tests and analysis, you repeat the risk assessment, you continue to find the weakest parts of your spacecraft, and you add shields or fly the vehicle or set up your detection system, your inspection, and your repair system for where you need it, you know, based on your risk assessment.
Well, the first lesson learned, of course, was that, you know, the debris environment, you know, is a hazardous environment. And actually it took us, you know, the agency, you know, 10 or 15 years to realize the degree of danger and the fact that, of course, that hazard is increasing now. But the most important lesson is that there are effective countermeasures to a significant portion of this risk, but they have to be considered and implemented very early in the design. For robotic spacecraft, we do assessments typically at PDR, and sometimes even that is too late, because at PDR you've already pretty much locked in some of your components, where you want to put those components. Some of the issues that we found is that because the debris hazard is unidirectional, if you have particularly sensitive components, be they for subsystems or be they for the primary payload, whatever it is, you may not want to have that out front. You may want to have that in the rear of the vehicle and have less sensitive components up toward the front of the vehicle in terms of its flight direction. But we found that a lot of countermeasures can be implemented at reasonable cost, reasonable effort, if you look at it early on and figure out what the risks are.